You guys are what, 6 weeks in, 45 weeks to go? Is that about right? I'm going to try and go easy on you, especially in this lecture. I'll just basically pace up and down and talk a lot in this lecture. First thing I want to tell you that there are detailed lecture notes for this course online. And I don't know the web address, but if you just Google David Tong quantum field theory, you'll find them easily enough. And I think Callum's arranged to have them printed out and given to all of you. Okay, good. So in particular, for most lectures, I'm going to write everything on the board. But for some lectures where it would be an essay on the board, which I've got no intention of writing, I'll just talk. And if you can't copy everything down, it's all written in these notes. Okay, so what we're going to do is walk you through the basics of quantum field theory for the next 3 weeks. And let me start just by kind of painting a picture about where quantum field theory fits in with what you know so far, which is basically just quantum mechanics. So you know from quantum mechanics that electrons act like waves and photons act like particles, and there's wave-particle duality and complementarity and all of this stuff. But basically, what we think of as photons and what we think of as electrons aren't that different from each other. They have different rest mass, they have different charge, but fundamentally the properties of these two objects are very much the same in a quantum mechanical world. But if we think about where these properties come from classically, that's rather strange, because they have very different properties in the classical world. So in particular, the electron, classically, we just think of as something you postulate. It's a fundamental particle, and we're then ascribing quantum properties to this. But the photon, or light, is not a fundamental property at all in the classical world. It's a derived property. The fundamental things are the electric and magnetic fields, and Maxwell taught us that ripples of these electric and magnetic fields gives rise to what we call light. So somehow we have this, this slight tension, because we know that electrons and photons should act roughly the same, but we also know that classically they come from very different backgrounds. So what we want to do in quantum field theory is try to reconcile this problem. Okay. By the way, do you guys ask questions? I don't know this. You do? Good. Okay. Good. Do ask lots of questions. Okay. So how are we going to reconcile this? Well, there's sort of two different options that you could envisage. You could imagine that it's the particles that are fundamental. So maybe it's the photons that are the fundamental object. And if you pack enough of them together, then that's what gives rise to what we call the classical electric and magnetic fields. Okay, that's one possibility. The other possibility that you could imagine is that it's actually the field that's fundamental, and that when you quantize the ripples of a field, that's what gives rise to particles. Okay. Now, it turns out that sort of both of these viewpoints have some validity. But it's certainly fair to say it's the latter viewpoint which has been the most useful. So this idea that it's not the particles that are fundamental. What's fundamental are fields, and that there are little ripples of these fields, and when you quantize those ripples, that's what we call particles. So for the electromagnetic field, that's what we call a photon. But now we're in a situation where we have to start introducing new fields for all the other particles that we know of in the universe. So we should introduce an electron field, and a quark field, and a W boson field, and a gluon field, and a neutrino field, and so on and so on. Okay? So that's sort of the basic premise of quantum fields. Okay. Good. So let me start by just sort of telling you why this is the right way of thinking. So why quantum field theory? Okay, so there's a bunch of different answers to this. Firstly, there's a zeroth order answer, which is for the same reason that people introduced fields in classical physics. And that's because of locality. The reason that Faraday and Maxwell and Einstein were thinking in terms of fields was so that if something happens here, an electron moves, we're not thinking that it physically influences something over here immediately. What happens is it influences a field in its vicinity. That field influences nearby fields. Everything ripples and ripples, and finally it influences something here. And there was never anything non-local happening. Okay, so that's true in classical physics, and it's also true in quantum field theory. But there's a couple of much deeper, more profound reasons to do with the Q in quantum field theory that also holds. So let me just try and explain what they are. Okay, so there's a couple of answers I want to give. So answer one is because all particles of the same type are indistinguishable. Okay, so you presumably know about this already from courses in quantum mechanics. It's the statement that if you have two electrons in front of you and you swap them around, then the state of the universe hasn't changed at all. Okay, it's changed up to a minus sign, but that minus sign isn't important for this current discussion. And you probably not even thought just how extraordinarily amazing this fact is, that all electrons are exactly the same as all other electrons. All protons are exactly the same as all other protons. It's sort of mind-boggling, but to put it in some perspective, you could get a proton which was created in a supernova, which you knew happened 5 billion years ago in some galaxy far, far away, and you could compare it to a proton that you freshly minted in a particle accelerator here on Earth, and they would be exactly the same. And not just exactly the same like the two red pool balls on the table outside are exactly the same, but exactly the same in an indistinguishable sense where if you swap them around, nothing changes. Okay, that's pretty amazing. Why aren't there sort of errors in the production process? How can something created all that time ago, or so far away, be exactly the same as something that was created here on Earth? So there's some words that you can drape around this, and the words are the following: that there's a fluid, a sea of stuff, sort of proton stuff, that fills the entire universe, and when we create a proton particle, what we're doing is we're taking a ball of this and we're molding it using quantum mechanics into a particle, and then it looks exactly the same as something over here because they're both made of exactly the same underlying stuff. Okay, so that's really the basic idea underlying quantum field. There's actually a bit more to this story, which is to do with that minus sign. You take two particles, two electrons, you swap them around. It's not exactly the same state, right? There's a minus sign in the wave function, which comes from Fermi-Dirac statistics and gives rise to the Pauli exclusion principle, which gives rise to all of chemistry and all of biology and all of life as we know it. It's that quite important minus sign. Now, in quantum mechanics, when you learn about statistics and its relationship to spin, it's really something which you're just told. You're told spin half particles should be fermions, spin zero particles or spin one particles should be bosons, and they don't pick up a minus sign. It's sort of an extra thing that you have to put on top of quantum mechanics. One of the things we'll learn in this course is why that is true, why this relationship between spin and statistics has to be true. And this will come out of quantum field. Okay, are there any questions about this? Okay, let me tell you answer two. Answer two. And it's because special relativity plus quantum mechanics implies that the number of particles you have in your system isn't conserved. By the way, how are these blackboards? If I write at the bottom here, can people in the back see? What's a good cutoff? Is that line's a good cutoff? Okay. So this says because special relativity and quantum mechanics implies that particle number is not conserved. From now on, I'll try and write above that line. Okay, what does this mean? I'll give you some examples about how this appears at the moment. Actually, I can tell you immediately. Google a picture from the RIC particle accelerator in Brookhaven, or better still, the star detector in RIC. What you'll see is this incredible explosion of particles flying out. There's about 10,000 particles that fly out of a typical collision at the RIC accelerator. These are created by firing together two gold nuclei, each of which has of order 200 nucleons sitting inside it. So it's a dramatic example of how particle number is certainly not conserved when quantum mechanics and special relativity, in this case high energies, combine together. What this means theoretically is that if you try to take the Schrödinger equation, which typically describes a single particle, and you try to generalize that to a relativistic version of the Schrödinger equation, which still describes a single particle, you ain't going to make any progress. Something's going to go wrong. Now, I just learned that on Thursday and Friday, Malcolm Perry told you how to take the Schrödinger equation and generalize it to relativistic examples of the Schrödinger equation, the Dirac equation, the Klein-Gordon equation. If you were to treat those as single particle equations, that is, the psi that appears there, you were to think of as the wave function for a single particle, you won't make any sense of that equation. Okay, I think Malcolm just sort of skirted around some of these issues. But you'll see that things go horribly wrong. You have to make sense of negative probabilities. No one knows how to do that. You'll find that you have infinite towers of energies which are unbounded below, and it's not quite clear what to do with that, although you can sort of just about get around it. You'll find that even though you think, because it's relativistic, the equation is causal, you'll find effects propagating faster than the speed of light. And what's happening is that in trying to write down this single particle relativistic wave equation, you've missed all the key physics, and this is the key physics. It's that there is no relativistic system with a fixed number of particles. Typically there'll be swarms of particle-antiparticle pairs around this fixed, this single particle you started with. So let me just write down something quantitative about this. Okay, so consider a particle trapped in a box size L, and we know that Heisenberg tells us that we don't know the momentum of that particle. There's some uncertainty, and the uncertainty is of order h bar over L. Okay. But if we're in a relativistic context, then one guy's momentum is another guy's energy. These are things which just transform into each other under Lorentz transformations. So somebody in a different frame is going to see some uncertainty in the energy of the system. So plus relativity going to tell us that there's an uncertainty in the energy which is of order h bar times c over L. But when the uncertainty of in the energy is getting so large that it's comparable to the mass of the particle you started with, then there's enough uncertainty for you to start creating particle-antiparticle pairs out of the vacuum. And I put the two there because typically you do need to create these things in pairs. Okay, the upshot of this is if you try to localize a particle in a small enough box, where I've dropped this 2 because this is all sort of order of magnitude estimates. But if you try to localize the particle in a box which is smaller than h bar over the mass of the particle times c, then it's not even possible to say that there's a single particle anymore. Because within that small region, there's a very likely chance that if you try to detect the particle, you may instead detect one of the particle antiparticles, which has just popped out of existence from the vacuum around it. So the length scale that appears here is called the Compton wavelength. And the way to think about this is that it's basically the maximum length scale at which it makes sense to talk about a particle at all. Because if you start exploring the particles at length scales smaller than this, what you're going to see instead is a swarm of particle-antiparticle pairs that surround the particle. Okay? Remember, there's another length scale associated to quantum mechanics of particles, and that's the de Broglie wavelength. This is much, much smaller than the de Broglie wavelength. Right? That's h over p, the non-relativistic momentum. So a good way to think about it is that the de Broglie wavelength is where the particle first starts to exhibit wave-like properties, and the Compton wavelength is where the particle sort of ceases to make sense as a particle at all. It's really, in some sense, the size of the particle. Okay, are there any questions about this? So these are the two reasons why we need to work with quantum field theory. Because all particles are the same, all particles of the same type are the same, and because particle number is not fixed in a relativistic context. Questions? No? Okay. I told you why quantum field theory is necessary, but I haven't yet told you what it is. So let me now say a couple of words about that. Okay, and so the important thing to stress here is that conceptually there's nothing really new in quantum field theory beyond what you've already seen in quantum mechanics. So what do you do in quantum mechanics? You figure out what the classical degrees of freedom are, and you promote those classical degrees of freedom to operators which act on some Hilbert space. So exactly the same is true here. The classical degrees of freedom are a field, and you take that field and you promote it to operators which act on some Hilbert space. What that means is that we have a field which is an operator-valued function over space. Okay, so quantum field theory is the quantization of the classical field a good example of a field to keep in the back of your mind are the electric and magnetic fields, classical electromagnetism. So the basic object is an operator valued function of space. Okay, so classically, every point in space has a field value associated to it. Quantum mechanically, every point in space is going to have some operator associated to it. This operator is going to be acting on basically a Hilbert space. Okay? This immediately tells us one of the major problems with quantum field theory, The problem is that there's an infinite number of points in space. Infinite number both that way, because space is infinitely large, and an infinite number this way, because space is a continuum. So what this means is that we're dealing with an infinite number of degrees of freedom. And that infinity is going to come back and bite us many, many times in understanding quantum field theory. And it's really where all the richness and beauty of quantum field theory is in making sense of that infinity. Okay, so that's what quantum field theory is. Finally, I should just tell you what it's good for. And the answer is really basically everything in theoretical physics. Quantum field theory is simply the language in which we write down the laws of physics. So this is true in high-energy particle physics, and that's because we're being at high energies, we necessarily have to include special relativity, and as I've told you, when you have special relativity in quantum mechanics, particle number isn't fixed, and we're obliged to work with quantum field theory. It's also true in non-relativistic settings. If you're working with condensed matter, where you have swarms of strongly interacting or weakly interacting particles, the correct description, even though particle number may be fixed, is still typically in terms of quantum field theory. Okay? It's true that we need to work on this with cosmology. The whole story of density perturbations in the CMB is an application of quantum field theory to curve space-time. If you're interested in quantum gravity and string theory, all of string theory is basically just quantum field theory. And even if you're interested in pure mathematics, and somehow Witten's legacy to the history of physics is mostly an application of quantum field theory to astonishing new results in mathematics. Okay, so you have to pay attention in this course, is what I'm telling you. Okay, still no questions? Yeah, please.
The reason why you have to think about quantum theory is this, I mean, I don't know what you mean by quantization of a classical field, but it seems like that's a very approach, like classical approaches, and like in quantum mechanics, it's the sort of approach that you take going from kind of classical mechanics to quantum. But you can also think about it as representations and other structures that are kind of more self-consistent and maybe not obvious from the classical case, but that make more sense kind of as a whole theory.
That's true, and we're not going to say too much about that kind of approach in this course. And typically, the one place where this has been very successful is sort of throwing out this part and just trying to jump straight into this, is in 1+1 dimensions, and things called conformal field theories in 1+1 dimensions, where there's enough algebraic structure there to make a lot of progress without having a classical theory at the back of your mind. In some sense, the ADS-CFT correspondence, which you'll probably learn about after Christmas, is another example of this. And there are groups of people who try to work on, axiomatic quantum field theory. I think apart from in the two-dimensional case, the results haven't been stunning for that. So certainly we're going to take this view and start with classical fields and work forward. Other questions? No? Okay, let me just give you a guide to the literature. There's a lot of quantum field theory books on the market. So I'm just going to go through a few here that I know. There's one which I just think is certainly the one you should have. And this course is going to be based mostly on the first 5 chapters of this. So it's Peskin and Schroeder. It's not an easy read. I mean, they do things in detail. They explain it well. But quantum field theory is a hard subject, and they don't fool you. You'll have to work to go through it. But it'll be good for this course. It'll be good for the next course. It will be good for the standard model course, and you'll need it if you do research. So this is really, I think, the number one book. There's a bunch of other books with sort of some redeeming features. Go through. Let me tell you about this one. This is a book by Ryder. It's basically very gentle, and he'll explain things well and go very slowly. It is an easy read, but after you've learned it, you probably won't open it again. So it's a great book to learn from, but not that useful for research afterwards. But as you're all learning, I think this is something you should be opening regularly. Then there's some other interesting books. Stephen Weinberg. You know this guy, right? He's one of the smarter Nobel Prize winners in the last 50 years. So he has this 3-volume series on quantum field theory. Volume 3, supersymmetry. Just don't bother opening it. There's better books to read on supersymmetry. But volume 1 and 2 are not bad. Actually, that's the wrong. They're really excellent, but a little bit quirky. So there's this story I've heard. I don't know if this is true. Weinberg has this book on general relativity. And I'm told that he wrote the book on general relativity in order to learn general relativity. And the result is I think, a completely fantastic textbook. And I really like that book. In contrast, when he wrote this, I think he knew more about quantum field theory than any other person on the planet. And it kind of shows. He takes this interesting route through the subject, lots of insight, lots of things that you won't find anywhere else, but at the same time, it's not that useful to learn from. So if you wanted a different take on things, I would highly recommend it. Certainly later in your careers, I suspect you'll be dipping in a lot, but to learn from, maybe not the best. Then there's Z's book. This is my favorite book on quantum field theory because he simply lies to you all the way through. And in a good way, for your own benefit. He makes everything easy. He sort of says that, yeah, you just do this and you just do that, and you'll really get the big picture of what quantum field theory is about, but I'm not completely sure you'll be able to compute cross-sections for the standard model after reading this book. But you'll certainly understand things very well. So this book with Peskin and Schroeder, I think, is a good combination. This brings me to one other point about quantum field theory. There's 2 ways that people teach quantum field theory. So one way is sort of what I've stressed here. You take a classical field and you promote the degrees of freedom to operators. It's called canonical quantization. The good news is that it's basically exactly what you've done in quantum mechanics already. The other good reason for doing this is that you get to see the particles coming out of the fields sort of very directly. So this relationship between fields and particles is going to be a big part of this course. At some point, however, doing calculations this way gets very, very difficult. And so there's a better way. There's a better technique, which is the path integral quantization, which I think Malcolm told you about last week. Is that right? Okay. So the path integral quantization of quantum field theory is much more powerful. It's much more simple. It does, however, sweep a lot of important subtleties under the rug. The rug in this case being an infinite dimensional measure that sits in front of the path integral. So what usually happens in a quantum field theory course is you start off using the canonical quantization, and at some point you have to make the decision to just jump and use path integrals and carry on. And the question is when you do that jump. So as we're teaching you 2 quantum field theory courses, the jump is going to be seamlessly in the middle of the 2. So I won't mention path integrals in this course. The next course is going to be all on path integrals. This is the way that Peskin and Schroeder do it, and like I said, we're more or less going to follow that. So this book by Z makes the jump in the beginning. The first chapter's on path integrals, so it means that although it's extremely good, you'll just have to be familiar with path integrals before you understand it, but you all are, right? So it's good. Okay. And finally, there's another book which takes the same route. It's all path integrals from the beginning. I think it may even be phi cubed theory in 6 dimensions from the beginning. It's by Srednicki. Again, it's just really clear and a good book. On top of this, that's probably overload already, but there's loads and loads of good online resources. Really excellent lecture notes that various people have written. So if you go to my webpage for this course, which again, just Google David Tong quantum field theory, there's a whole list of notes at the bottom there, which you can pick and choose.
On the wiki already.
Sorry?
On the wiki already.
Brilliant, okay, and it's on the wiki. Good. Okay, what else do you need to know? How are we doing for time? It's 35 minutes. Let me tell you some history. It's always just good to have a bit of context laid down for you. So quantum field theory started immediately after the discovery of quantum mechanics, late 1920s. These giants of quantum mechanics, people like Heisenberg and Pauli, Dirac, of course, they were all trying to quantize the electromagnetic field. Basically, for the reasons I mentioned at the beginning, they realized that had to be the correct description. By the way, the guy who first understood the way particles come from fields was probably Jordan. And he didn't win the Nobel Prize, I suspect, because he was a rather enthusiastic member of the Nazi Party. And this was, at a time way before it was fashionable to be an enthusiastic member of the Nazi Party. So these guys sort of laid the foundations of quantum field theory. Late 20s, all the way through the 30s, were trying to understand the way to quantize a field. And they basically failed because of this infinity, because they couldn't really make sense of having a theory with an infinite number of degrees of freedom. So if you look, there are these very interesting quotes from people like Dirac at the end of the 1930s saying, I think we've all now decided to junk quantum electrodynamics. Thank God we never have to go back and look at that again. It's an ugly theory. So that was basically the situation leading into the Second World War, was that people had tried and laid down the framework for quantum field theory, but not really managed to succeed to make sense of these infinities that arise. I should say, what we're going to do in this course doesn't go a lot beyond what those people did in the 1930s. It's really just the very basics. We're kind of going to take a route which just avoids mentioning these infinities whenever possible. Okay, so then the next big success came after the war. It was the new breed of physicists, Tominaga, Schwinger, Feynman, Dyson, and they understood how to make sense of these infinities through a process that they called renormalization. They developed the theory of QED. It was phenomenally accurate. There'd never been a theory like it, which agreed with experiment to such incredible number of significant figures. But even then, I think there was this underlying suspicion about what they were doing. This idea of renormalization to get rid of some infinities. You read statements that it was like sweeping infinities under a rug, that Feynman called it a dippy process. People were uncomfortable with this. So by the 1960s, it was really falling out of fashion. People were discovering new particles all the time, mesons and baryons, and strong resonances. And somehow the idea you should have a field for each of these was a little bit upsetting to people. And so other techniques were being developed. Techniques sort of a little like what you were suggesting. You junk the classical field and you go to something more abstract. In that case, it was the S-matrix or bootstrap methods or things like this. And I think in that time, in the 60s, there were probably only a handful of people working on quantum field theory. And then we get to the 1970s, and this is the golden age. Asymptotic freedom tells us that really it's a quantum field theory that's built underneath the strong force and gives rise to all these dozens, hundreds of particles that were seen. These infinities that are there from the beginning, they're finally understood in a deep and profound way, starting with work by Kadanoff, by Wilson, and this really gives rise to I think the most important part of quantum field theory is understanding these infinities using what's called the renormalization group. Meanwhile, there's progress on understanding the way geometry and topology fits into quantum field theory, and I think from then it's been clear that it's the framework in which nature is written, certainly on the energy scales that we've probed so far. Okay. Good. So, just a few basic things before we really get going. Let me tell you about some units and scales. Okay, so it's usually said that there are three fundamental constants which nature gives us. It's completely wrong, but I'm going to say those words anyway. There are three fundamental constants that nature gives us. And so this is the speed of light, h bar, and Newton's constant g. The units is the speed of light obviously has length over time. H bar has units of joules seconds, which if you write in terms of length, mass, and time is the following. And meanwhile, Newton's constant has the following units. So throughout this course, we're going to work in units in which h bar is equal to c is equal to 1, which means that, and what this really means is that we can basically translate between units of time and units of length just by putting in factors of c. Sometimes in courses on general relativity, people will instead set the Planck mass to 1 or g to 1. I'm not sure if Rob does that, but we're going to keep this unfixed. Okay, so this means we can express everything in terms of mass, or equivalently energy. And the usual particle physics energy scale is electron volts, or often MeV, GeV, or TeV, but some kind of electron volt. So then to convert back to meters, seconds, whatever, we need to insert C's and H bars just to get the units right. Okay. So for example, we've seen one of these equations already. The Compton wavelength is basically the inverse of the mass. This is a length scale. This is a mass scale. If you work out what units you have to, or what quantities you have to put in to get the units right, there's an h bar on the top and a c at the bottom, which is exactly what we saw before. So this is length. So for example, if you look at the mass of the electron, using this relationship here, this converts to a length scale, which is 10 to the minus 12 meters. Okay, so there's a useful exercise. Maybe Nima walked you through something like this, but you should do the following. Just figure out what the energy scale is associated to the size of the universe, the solar system, and say the atomic scale. Okay. Also figure out what the length scale is associated to the cosmological constant, the LHC, I don't mean 30 kilometers, I mean inverse TeV, and the Planck scale. Okay. Okay, so if a quantity has mass dimension mass to the d, we'll write sorry, I should have said it for quantity x. Okay, so you'll see things like this a lot. So some quantity has dimensions of mass to the d, put it in square brackets, and that's its dimension equals d. Okay. So for example, if a quantity really has dimensions of length, that quantity here, d will be minus 1, because length is inversely proportional to mass. Is that clear? Have you seen things like this before? Yeah? Okay. So in particular, Newton's constant, which we haven't talked about yet, has dimensions minus 2. And so we use Newton's constant to define an energy scale after we've said h bar equals c equals 1. And that energy scale is the Planck mass, which is 10 to the 19 GeV. Okay, so like I said, it's good to just work out and remember what all the relevant length scales and energy scales are, starting from the Hubble scale and going all the way down to the Planck scale. Okay? And what the ratio is between those two. Okay, any questions about this introductory stuff? Yeah.
Sorry, why G equals h bar times c divided over n?
So this is a definition of what we mean by the Planck mass. Okay, so the units are right. You know, the units of this were well, the units are correct. Joule second meters divided by seconds divided by some mass scale. So after you've set h bar is equal to 1, Newton's constant defines for you an energy scale or a mass scale. You know, energy scale is the same as a mass scale because E equals mc squared, but c is 1, so it's the less catchy E equals m. Yeah. Other questions? Okay, so the next goal is to just describe to you some simple things about classical field theory. So I set some problems on Friday just to see if you were happy with ideas of Lagrangians and Hamiltonians. So let me just ask, how many people were happy with those? How many people weren't happy with? Is it all good? If I just talk about Lagrangians and Hamiltonians, everybody's going to be okay. Okay, good. So So this is section 1, classical field theory. Okay, so I should warn you now, we're going to need various bits of classical field theory, things to do with different representations of the Lorentz group and gauge symmetry. And the plan is not to give it to you all at once, but just to give you the minimum stuff that we need. Then we'll go on to quantum field theory. And then as the course progresses, we'll just start to introduce more and more stuff from classical field theory that's necessary. So let's just start with some definitions. So a field is a physical quantity defined at every point of space and time. As with all definitions in physics, it's a bit of a lie, but you know, those lies will become apparent as we move forward. Okay, so I want to contrast this with what we usually think of in the first kind of courses in quantum mechanics, and indeed the first kind of courses in classical mechanics. So in classical particle mechanics, there are a finite number of degrees of freedom. Okay, so you have some degree of freedom that we'll call Q. It's a coordinate. It's sometimes called a generalized coordinate in this Lagrangian setup. And, it's things like the position of the particle. Okay? There's typically some label on these. For example, it's the position of the particle in that direction or the position of the particle in that direction, and so on. But there's some finite number of labels you attach to this. And the goal of classical mechanics is basically to figure out what these functions are, i.e. how the positions of particles change as a function of time. So in field theory, we have an infinite number of degrees of freedom. Okay, so we have a field which is a function of space and time. There could be some finite labels that we'll just call A here. But in particular, X, the position, is again just a label for the degree of freedom. It tells you the degree of freedom at this point in space or the degree of freedom at this point in space. Okay, so if you like, position's been relegated in quantum field theory. In quantum mechanics, position was this dynamical variable for the particle. By the time we get to quantum field theory, it's not a dynamical variable at all. It's now just a label, and not too different from all the other labels that we're going to put in. Okay, so some simple examples. Yeah, exactly. That's not an operator anymore, right? So those uncertainty relations between x and p, x is just a label. There's nothing uncertain about it. So the question of how we then go from quantum field theory, which is fundamental, to usual ideas of quantum mechanics takes a bit of thinking about. And I may set this for an exercise maybe at the end of this week.
That definition of field you had earlier, does that then mean that things like scalar potentials are fields and do that?
Yeah, that's why it was a lie, because I said physical, but actually there can be caveats to do with gauging variances.
Well, why I asked is because typically fields are introduced as vector quantities, but I mean, are scalars.
Oh, I see. So absolutely, scalar is going to be the first kind of field.
Okay.
Think of a temperature field. At every point in this room, to be coarse grained, there's a temperature that we can associate to it. That's a field which evolves under certain diffusion equations motion. The reason it's alive because the scalar potential in electrodynamics isn't something physical. It's not something you can measure because it's potential differences you measure because of gauge variance and so on. But we'll come to these issues as well. Okay. So as you said, the fields that we're most familiar with are vector fields. The electric field and the magnetic field, they're functions of x and t, but x is just a label for this field. It's not the dynamical variable. And the I index here just goes from 1 to 3 and tells you the direction in which this field's pointing. Okay. Okay, and I'm writing this down because I'm going to set an exercise on this. Okay, so this should be familiar, but remember these fields obey certain equations, Maxwell's equations. You can solve 4 of those equations, you can solve 2 of those 4 equations immediately if you rewrite these 6 fields, 6 because there's 3 here and 3 here, in terms of these 4 fields using this. Okay, again, hopefully familiar to everybody. Is this not familiar to anybody? Yeah. Okay, so what we want is we've got these fields that we've specified, and the first thing we want to do is just understand how these fields are going to move, how they're going to evolve. And there's several different ways that sorry, my bad. Yeah, thanks. I'm going to make lots of mistakes like that, so shout, okay? So we want some way to specify how these fields move, just classically, before we get to the quantum theory. So we could just write down the equations of motion for these fields. They would be Maxwell's equations in this case. But actually, there's a much more concise way of capturing the equations of motion, and that's using the Lagrangian. We could also use the Hamiltonian, and we'll see shortly why the Lagrangian is better than the Hamiltonian for fields, certainly for relativistic fields. Okay. So the dynamics of the fields is governed by a Lagrangian which is a function of, well, the fields their time derivatives. So if you think back to standard particle mechanics, the Lagrangian is typically a function of the positions of the particles and their velocities. So the analog here is the value of the field, the time derivative of the field, but now the field is also a function of space. So we're going to include in this spatial derivatives of the field. And we're going to write the Lagrangian in the following way. So the Lagrangians we're going to consider are integrals over all of space of this function that I'll call curly L instead of a straight L. So from the Lagrangian we build an action sorry, I'm just going to slip under the line here. Yeah, I'll just mention that. So the action is the integral over time of the Lagrangian, but because the Lagrangian itself is the integral over space, the action becomes the integral over space and time of this thing called curly L. So this curly L is really called the Lagrangian density. But it's one of these things where you're told it's called the Lagrangian density when you first encounter it, and from then on everybody just calls it the Lagrangian. But occasionally you'll read a paper where people have to be specific about the Lagrangian or the Lagrangian density, but this is what's meant. Okay, so a quick note. Yeah, please.
Double derivative, two derivatives of phi.
I'm about to write down that reason. The answer is no. There's no reason at all. But there is. We'll see. So in particle mechanics, L is a function of Q and Q dot, but it's not a function of the acceleration. You know, the whole framework of Lagrangians, as we first learn it, requires that it's only a function of Q and Q dot. So in field theory, L is a function of phi dot. Actually, let me write this in words. It might be. Should not depend on phi double dot Okay, so you see that as I've set this up, that there's really still a difference between the way that phi depends on space and the way that phi depends on time. Space is just a label, and what we're interested in is how a given field configuration at a fixed time evolves to a field configuration at a later time. Now, for the same reasons as in particle mechanics, the Lagrangians shouldn't depend on the acceleration of phi. It shouldn't depend on phi double dot. But there's no reason, in principle, why it can't depend on second derivatives of spatial derivatives of phi. And there's various cases that you'll come across where the Lagrangians will depend on spatial derivatives of phi. Certainly in condensed matter, where there's no reason that space and time have to be on the same footing. There's no Lorentz invariance. It's not unusual at all to find Lagrangians with these kind of terms. However, as you could imagine, what we're really trying to do in this course is unite special relativity with quantum mechanics through quantum field theory. If we're going to do that and have any relativistic theory, then space and time had better be appearing on equal footing. And so for that reason, we're only going to consider Lagrangians that are a function of the first derivative, spatial derivative of phi, but not two derivatives. Okay? Is that the question you asked?
So why can't the Lagrangian density depend on phi dot dot?
Oh, so you know, it's basically the reason that you need two initial conditions, the initial position and the initial momentum, in order to dictate the rest of the motion of a particle, or indeed of the field. Yeah. Please.
So you mean in the field theory, only space x is a label, t is not a label?
T is exactly the same footing as it is in particle mechanics. It's the thing you want to solve for.
You mean t is a physical quantity in the field theory?
I'm not sure what that question means. I know in some sense it's on the same footing as x, but in making the leap from particle mechanics to field theory, it's best to think of x as a label, and then realize later that it's possible to put it on the same footing as time. I think that's the right way to say it. I'm going to say a few more words about this in the next 5 minutes, so maybe you could ask again after that if you want. Other questions? Okay, so let me just remind you about the way the principle of least action works. I know that was the what I asked in the homework exercise, but it's a little bit different in field theory. So let me just tell you how to do that. Okay, so So we determine the equations of motion by the principle of least action. Okay, so we vary the action by considering, let me write it down, it'll be easier. Okay, so let me just remind you how this principle of least action goes, because it's a little bit of a twist from the usual ideas of classical mechanics. Usually in classical mechanics you say, well, the particle starts here and it has this momentum, and I want to know where it's going to end up. In the principle of least action, the way you phrase it is a little different. You have to input two initial conditions, but rather than having the initial conditions being where the particle starts and how fast it's going, the initial conditions are instead not really initial at all. It's where the particle starts and where the particle finishes, and they're your two conditions. And then you say, well, I consider every single possible trajectory the particle could take between here and here, and I ask which one minimizes the action, and that's going to be the true path that the particle takes. That agrees with F equals ma, Newton's equations of motion. So what do we do for fields? For fields, it's the same. We fix the value of the field. Let's get this right. We fix the initial value of the field and the final value of the field. And we want to know, how is this value of the field configuration going to evolve into the other one? Well, what we do is we vary the action, and we insist that it's an extremum of the action. So this is varying the action for a field. It's exactly the same as the equation you would have for a particle. There's this finite label A here. What's new is that the action is now going to depend on phi dot and grad phi, and so I've included both of them in here with this mu index. Okay, so now the usual trick is you do an integration by parts. You move this derivative over to here, but notice now it's a time and a space derivative, not just a time derivative. And then you pick up the boundary term for your troubles. The integral is over everything. Sorry?
You on the boundary term?
Yeah. So there was this du here, and what I did was I took this outside of everything. That's this term, and then subtracted the du just hitting this.
Still haven't integrated yet.
Maybe am I just missing these brackets? Is that the,
Oh.
yeah?
Well, that would include the boundary term in your intro,
Yeah, yeah. I've just integrated my parts at this point. I haven't thrown anything away.
but I thought the boundary term
It goes on the next step.
Just wait 30 seconds.
Yeah, less than that. Okay, so now this vanishes. But why does it vanish? Well, it vanishes for any variation delta phi a xt. We actually need two reasons now why this vanishes. So in the usual particle mechanics, it vanishes because you consider all possible paths between these 2 points, keeping the endpoints of the path fixed. Okay, but here's the variation of the path. But because there's a total derivative here, it's the variation of the path at the boundary, which means at initial time and final time. So it vanishes because this vanishes. But now we've also got to worry about spatial infinity as well. So the correct statement is that this term vanishes for any variation that decays suitably fast at spatial infinity and then obeys what you usually require, which is that you only consider variations of the field which are fixed at the initial and final times. So this says t initial and t final here. Okay, then finally we've got the equation that delta S is equal to this integral here, and that the equations of motion should be equivalent to asking that delta S is 0. In other words, this bit inside here vanishes. So these are the equations of motion for a given, I guess I should still have that A index on everything. For a given Lagrangian, which is a function of a set of fields, these are the equations of motion. Okay. Let me just do one example very quickly. So I'll do one example, and then I'll just set a couple more as exercises for you to do at some point. So the example is going to be the Klein-Gordon equation. Okay, this is the Minkowski metric, and I think in contrast to your general relativity lectures, it's going to be mostly minus. You just have to get over this. I mean, everybody's going to use a different signature. it sort of makes sense here. Let me just explain why it's a good. It's a good convention for quantum field theory. If I expand this out, it looks like the following. So think of this in terms of your usual Lagrangians that you first learned about. What's the usual Lagrangian? L is equal to T minus V, kinetic energy minus potential energy. So what do we have here? This is the kinetic energy of the field, phi dot squared, how fast it's changing in time. But then the potential energy has two pieces. There's the piece here that I've just introduced, some phi squared piece, saying that if the field gets bigger, you pay a potential energy price of order phi squared. And then there's also a gradient piece. The gradient piece comes with a minus sign because this whole thing, gradient plus m squared phi squared, should be thought of as the potential energy. Okay? So the reason this signature is useful, and really it's useful because it's energy which is positive rather than length scale. But in particular, it means that when you write down kinetic terms, they just come with a plus here. Okay, plus d mu phi, d mu phi. If you were to have the other sign, you'd have to put a minus in front of this kinetic term for the Lagrangian. Okay, so what are the two? So figuring out the two terms in the Euler-Lagrange equation, you just have to differentiate this. And if you were to plug this into the Euler-Lagrange equations, you'll find this, which is the same thing as this. So this is what's called the Klein-Gordon equation. It was actually first written down by Schrödinger. It was Schrödinger's first attempt to write down the Schrödinger equation because Schrödinger knew about special relativity and figured if he was going to write down some new fancy equation, it better agree with special relativity. Okay, in the end, it's not the right interpretation. Okay, you shouldn't think of this in the same way as you think of the Schrödinger equation. This phi here has nothing to do with the wave function in quantum field theory. Okay, sorry, nothing to do with the wave function in quantum mechanics. Nothing at all. This is just a scalar field which has some value at every point in space, and this is an equation which is telling you how that scalar field is changing with time.
How did you get that first equation? Sorry, on the left-hand side of the board.
This guy.
Yeah.
Yeah. If you're not happy with the indices, so you know, the point is I can.
Right. You raise
I
the
can raise
indices
this,
in your
but then you might think, you know, have I only got one d phi with it down, so am I cancelling this off? Is that the problem, or are you?
Oh.
See, I'm differentiating with respect to a d mu.
Oh, I see. So you just pulled away one of them and that was the other.
But you do that twice because it's a d phi squared. If you're not happy, I recommend the following. Expand this out as phi dot squared minus grad phi squared. Expand out the Euler-Lagrange equations in the same way.
Yeah, I think I see it now.
And then plug it in.
Yeah. It just didn't immediately. Well, I'm sorry. Give me a moment.
Good. Yeah, so let me stress again. If you've seen this Klein-Gordon equation before in quantum mechanics, ignore it. This isn't a wave function. Okay. Okay. I'm going to set a couple more exercises along these lines that you can do this afternoon or maybe maybe tomorrow, just simple Lagrangians and trying to figure out what the equations of motion are for them. Among them will be the Lagrangian for Maxwell theory, which you may or may not have seen before. Okay, are there any questions? Please.
You said that the variation of the field at infinity has to go to 0.
Yeah.
Time infinity. What does that say about the fields themselves? Like, are we only going to consider fields that go to 0 at infinity?
I'll say yes, because it's going to make life a whole lot easier. There will be situations, of course, where that's not what you're interested in a given problem, and you'll have to deal with it at that time. But
Right,
in this course,
But like this Euler-Lagrange equation, is it only valid for fields that go to 0?
I think a more correct statement is you have to add extra terms to the action to
Okay.
the end.
Okay.
There's something called the Gibbons Hawking term in general relativity. I don't know if you come up.
Right.
And it's just start with the Einstein-Hilbert action. It doesn't actually define a good variation principle. You have to add a boundary term to
Okay.
these kind of issues. Any other questions? Okay, let's get coffee.